No. 1L22152KE1 Series. Instruction Manual. Robot Language Operation by TP. Read and follow these instructions and all safety blocks carefully. Have only trained and qualified persons install, operate, or service this unit. Give this manual to the operator. For help, call your distributor. Be sure to read instruction manuals before use. Thank you for selecting the arc welding robot All Mega Series. All Mega Series are the robots with high performance and various functions developed by making full use of the latest technology. Since the knowledge of welding peculiar to a welding machine maker is applied to both hardware and software, we are sure that each user can be fully satisfied in order to use the superior performance and the abundant functions safely and fully. Be sure to read the following instruction manuals including this manual and other attached documents, and understand the knowledge of the machines, safety information, and notes thoroughly. Instruction manuals related to the manipulator/per hour series, and the robot control unit FD11 are as follows. Standard manuals. Instruction manual type instruction. Manual no. Main contents. Quick start 1L21700 a point on safety, transportation and installation, turning the power on/off and manual operation, etc. Setup. 1L21700B. Safety precautions. Installing and connecting method. Starting up. Periodical inspection. Solution at the time of failure. Controller maintenance 1L21700K specifications of controller, explanation of each parts, and maintenance, parts list, etc. Manipulator NB4/NB6/NB15/NB6/NB20/NH51L11130 a specifications or maintenance of manipulator, parts, list, etc. Manipulator on B51L11312 a specifications or maintenance of manipulator, parts, list, etc. Manipulator on B166/NB210-1L11306 a specifications or maintenance of manipulator, parts, list, etc. Basic operations. 1L21700C. Explanation of manual operation, teaching, automatic operation, file utilities, backing up data, basic operations of arc/spot welding application, etc. External input/output 1L21700H interfacing method with external control device, list of I/O signals and start/halt the automatic operation, etc. Software PLC 1L21700J create program, input/output relay lists, list of command words, etc. Control and maintenance function 1L21700L edit logging, user check, troubleshooting, etc. Application manuals. Instruction manual type instruction. Manual no. Main contents. Application manual arc welding 1L21700F basic settings. Functions for arc welding, teaching, technique, etc. Application manual spot welding 1L21700E basic settings. Functions for arc welding, teaching, technique, etc. Instruction manuals are available other than the above for each optional function that you have purchased. Notes 1. Specifications and information contained in these manuals are subject to change at any time without notice. 2. The screen display of a teach pendant shown in the manual are described as examples, which may be different from the actual ones. 3. Although we cautiously compiled this standard specifications to eliminate as much error as possible, we do not take any responsibility for damages resulting from neither direct nor indirect errors. 4. The manual is a part of robot products. When transferring or selling off a robot, be sure to append the manual. 5. No part of this manual may be reproduced without permission. 6. Prohibited altering or remodeling. Do not alter or remodel our products. You may get injured or have your equipment damaged because of fire, failure or malfunction caused by altering or remodeling the product. The warranty does not cover any altered or remodeled products. -1 notice. Notes on safety. Before installation, operation. Be sure to read Chapter 1 Points on Safety in Setup Manual and other attached documents thoroughly and acquire all the knowledge of machines, safety information, and precautions. Furthermore, before maintenance, inspection, and troubleshooting, be sure to read Controller Maintenance Manual and Manipulator Manual and other attached documents thoroughly and acquire all the knowledge of machines, safety information, and precautions. If operating machines in a wrong way, the accident resulting in various ranks of injury or death, or damage may occur. In order to call attention to wrong handling, the following 4 ranks of safety notes: danger, warning, caution, and important, are provided. Danger. Cases where a mistake made in handling is likely to cause the user to be exposed to the danger of death or serious injury and where the degree of the urgency imminence of the warning given for the danger to occur is at the high end of the scale including high level danger, -2 warning. Cases where a mistake made in handling is likely to cause the user to be exposed to the danger of death or serious injury. Caution. Cases where a mistake made in handling is likely to cause the user to be exposed to the danger of minor injuries or of property damage only. The following symbol is also used for particularly important checkpoints. Important. This is a particularly important checkpoint. Note that even the matters which are described as caution can result in serious accident depending on the conditions. Be sure to keep the safety notes since they describe very important matters. The meanings of serious injury, minor injury, and damage described above are as follows. Serious injury, injury which has the after effect by loss of eyesight, and injury, the burn high/low, temperature, and electric shock, fracture, poisoning, etc., and that which requires hospitalization and long-term treatment as an outpatient. Minor injury, injury which does not require either hospitalization or long-term treatment as an outpatient. A burn high temperature, low temperature, and an electric shock. Damage, direct and indirect damage in connection with damage of property and equipment. Contents. Chapter 1 Introduction. 1.1 Robot Language Operation by TP-. 1-1 1.1.1 Summary. 1-1 1.1.2 Frequent Use Terms. 1-2 1.2 Function Command. 1-3 1.2.1 Typical Function Command List. 1-3 1.2.2 Creation and change of pose constant by function command. 1-5. Chapter 2 Example of use. 2.1 Acquisition of robot position and posture. 2-1. 2.2 Linear operation through 4 points specified with coordinate values. 2-2. 2.3 Circular operation with specified center point 90-degree division. 2-3. 2.4 Detection of pipe center position. 2-5. 2.5 Circular operation with specified center point 45-degree division. 2-7 This is dummy page. Do not erase. Chapter 1 Introduction. This chapter describes the outline of teaching of robot language from TP. 1.1 Robot Language Operation by TP-. 1-1 1.1.1 Summary. 1-1 1.1.2 Frequent Use Terms. 1-2 1.2 Function Command. 1-3 1.2.1 Typical Function Command List. 1-3 1.2.2 Creation and change of pose constant by function command. 1-5. 1.1 Robot Language Operation by TP. 1-1. 1.1 Robot Language Operation by TP-. 1.1.1 Summary. Robot language is the program language which enables to customize the robot operation. Advanced robot movement which is difficult to teach by the conventional methods can be achieved by programming with the computational commands of the robot language. This function implements the one same as the robot language by recording the function command, fn from TP, Fig. 1.1.1 shows the procedure from teaching to playback using the robot language and Fig. 1.1.2 shows the procedure from teaching of the robot language by the function commands to playback. Teaching of the robot language assumes that an editor software of PC is used as shown in Fig. 1.1.1. Therefore, the robot language need to be forwarded between PC and this controller for every teaching modification and the operation is complicated. This function enables the robot language to be used by teaching only with TP. It saves trouble about teaching modification. Also, the image of Cartesian coordinate values of the robot is hard to understand. With this function, the current position of the robot can be recorded in the pose constant as the Cartesian coordinate values. Advanced robot movement which is difficult to teach by the conventional methods can be achieved by editing and recycling the pose constant at the time of playback which is taught with this Cartesian coordinate value. Editing robot language file using a text editor. Robot language F file. Program file. Control unit. Playback operation. Personal computer. USB. Compiling reverse compiling. Fig. 1.1.1 Procedure editing a robot language file using a text editor and playback operation. Program file. Control unit. Editing robot language file using function command. Creating pose file. Editing pose constant. Structured programming. Using pose constant in MoveX function playback operation. Fig. 1.1.2 Procedure editing a robot language file using function command and playback operation. 1.1 Robot language operation by TP. 1-2. 1.1.2 Frequent use terms. Table 1.1.1 Frequently used terms. Terms explanation axis angles. This is one of the pose expression methods of the robot. The robot pose is specified by specifying all the joint angles degree of the robot. For this controller, the coordinate system is represented by the right-handed scale. In the right-handed coordinate system, x-axis, y-axis and z-axis are specified in order of thumb, index finger, middle finger. The x-axis crosses the y-axis at right angles. The z-axis crosses them at right angles. Following four coordinate systems can be used as the basis for the robot pose. Type description. Mechanism coordinate system. This is in the center of base of the robot. Absolute coordinate system. This is the only coordinate system in the system. Work coordinate system. This is on the positioner. This is used as the basis for the synchromotion operation. User coordinate system. This can be applied at an arbitrary position. Coordinate system. X, Y, Z. Robot. World coordinates. Coordinates. Work. Coordinates. Cartesian coordinates value. This is one of the pose expression methods of the robot. This indicates the position and posture of the torch tip with reference to the mechanism coordinate system to be usually applied to the robot base. The robot language for this controller expresses postures with roll, pitch and yaw angle. User coordinate system is applied by the user to an arbitrary posture with the origin of an arbitrary position. User coordinate system can be defined on the basis of either absolute coordinate system or work coordinate system. Pose constant. In the robot language, the position and posture of the robot can be equated with the pose constant. Advanced robot movement, which is difficult to teach by the conventional methods, can be controlled by changing this pose constant and operating it as the robot target position. 1.2 Function command. 1 to 3. 1.2 Function command. 1.2.1 Typical function command list. The typical function commands, which can be taught from the TP as the robot language, are shown below. Please refer to the online help or the command reference for details of other commands and each command. Table 1.2.1 Typical slim command list can be taught from TP. Slim command FN name explanation. Let OR68 set shift value sets the shift data for the specified shift register. Add OR69 add shift value adds values to the specified shift register. Let 71 pose X substitutes values for the element X of the pose constant. Let E72 pose Y substitutes values for the element Y of the pose constant. Let 73 pose Z substitutes values for the element Z of the pose constant. Pose sov 74 pose sov saves the result of the pose operation in the pose file. Let V75 set integer variable substitutes values for the specified integer variables. Let VF76 set real variable substitutes values for the specified real variables. Use 98 select pose file selects the pose file. CHG coord 113 change coord. No, shift. Can select the user coordinate system number to use for shifting in the user coordinate system. Get 142 set real variable coordinate values. Stores the current coordinate value in the real variables of the specified numbers. Get pose 143 set real variable pose. Stores the pose data of pose constant numbers in the real variables of the specified numbers. Let pose 144 set pose variable stores the pose data of real variables in the specified pose constant number. Gets FT 145 volts. Set real var, shift, pose data of the shift register is stored in the real number variable. Get angle 157 set real variable ang, current angle value of each axis is stored in the real number variable. Lefty 161 arm config, left/front, selects the posture where J1 will be the left arm. System on the robot posture calculation. Righty 162 arm, config, right/back. Selects the posture where J1 will be the right arm. System on the robot posture calculation. Above 163 elbow config. Above. Select the posture where the angle between J2 and J3 will be less than 180 degrees on the robot posture calculation. Below 164 elbow config. Below. Select the posture where the angle between J2 and J3 will be 180 degrees or more on the robot posture calculation. Flip 165 wrist config. Flip. Select the posture where the angle between J3 and J5 will be less than 180 degrees on the robot posture calculation. Non-flip 166 wrist config. Non-flip. Select the posture where the angle between J3 and J5 will be 180 degrees or more on the robot posture calculation. SF0470 wire extension. Detects and corrects the dispersion of extension length of welding wire, and plays back the record position. SF1471 one direction search. Touch, can detect the deviation amount touch sensor. ZF1481 direction search. Laser, can detect the deviation amount, laser search. 1.2 function command. 1 to 4. If 602 condition. If then else, when conditions are met. Transfers control to then, when not met, to else. On 603 on go to jump. Transfers control to the line number or label written at the same sequence level as the numerical value indicated by the integer variables. For 604 loop start, this is a repeat command. Starts loop here. Next 605 loop end, this is a repeat command. Ends loop here. Modus or coord 626 modify user. Coordinate can update the user coordinate system. Ledley 628 set local integer variable. Values can be substituted for the specified the local integer variable. Ledolf 629 set local real variable values can be substituted for the specified the local real variable. Let coord 630. Let pose variable can set pose variables specifying the coordinate system. Let 632. Let pose element can set pose variables specifying the element. Let 633. Let shift element can set shift register specifying the element. Let 634. Let variable can copy the value of variables. Add 635. Add pose variable can add shift variables to pose variables. Add v637. Add integer variable can add integer variables. Add vf638. Add real variable can add real variables. Sub v639. Subtract integer variable can subtract integer variables. Sub vf640. Subtract real variable can subtract real variables. Mul v641. Multiply integer variable can multiple integer variables. Mul vf642. Multiply real variable can multiple real variables. Div v643. Divide integer variable can divide integer variables. Div vf644. Divide real variable can divide real variables. Move x645. Record move x can record move x command. Timer 650. Let timer function returns the time which has elapsed since the power was turned on. SQR 651. Let SQR function obtains the square root. Sin 652. Let sin function obtains sin f. Cos 653. Let cos function obtains cos f. Tan 654. Let tan function obtains tan f. Atten 655. Let atten function obtains atten f. Atten 2 656. Let atten 2 function obtains atten 2 f. Abs 657. Let abs function obtains the absolute value. Min 658. Let min function obtains whichever is lower. Max 659. Let max function obtains whichever is higher. 1.2 function command. 1 to 5. 1.2.2 Creation and change of pose constant by function command. The characteristics of robot language are that the pose constants can be recorded as the target point of movex after pose constants, which are the move command of the robot, are created and changed. Table 1.2.2 A method of recording pose constant. A method of recording description record key *1, same as the normal task program. A method to operate manually the robot to the target point and record the robot position and posture in the pose constants. Edit screen *1, a method to change the contents of the recorded pose file with the robot. Coordinate value x, y, z, r, p, I. Specify coordinate value by function command. Using function command let pose variable let coord fn630. A method to record pose constants with the coordinate value in the arbitrary coordinate system. *1, available only when enabled, is set for service utilities -1. Teaching / playback condition -13. Record of pose. When the function command let pose variable let coord fn630 is used, the position and posture of target point to be recorded in the pose constant can be specified numerically with coordinate values in the arbitrary coordinate system. Fig. 1.2.1 Function command let pose variable let coord fn630 teach menu. Since the pose constants can be recorded with the coordinate values in the workpiece or user coordinates, pose constants can be recorded numerically from the TP referring to the dimension of the workpiece drawing, and the task program can be created. Also, since the pose constants of target point can be specified numerically with the coordinate values, the robot need not to be operated to the taught position by manual operation. If it is simple work, the task program can be taught in a short time. For the record of pose constant by the record key and the change of pose constant by screen editing, refer to 3.3 Creating pose files of robot language in the option manual. Chapter 2 Example of use. This chapter explains the robot language function for arc welding operation with concrete descriptions. 2.1 Acquisition of robot position and posture. 2 to 1 2.2 Linear operation through 4 points specified with coordinate values. 2 to 2 2.3 Circular operation with specified center point 90-degree division. 2 to 3 2.4 Detection of pipe center position. 2 to 5 2.5 Circular operation with specified center point 45-degree division. 2 to 7 2.1 Acquisition of robot position and posture. 2 to 1 2.1 Acquisition of robot position and posture. Stores the TCP position / posture x, y, z, r, p, I of the robot in the real variables. This is used to numerically grasp the position and posture of the robot. This section describes examples which store the robot TCP position and posture when the wire touches the workpiece in the real variables in the system having touch sensor FDWD. Fig. 2.1.1 Detecting the position after touch sensing procedure. Table 2.1.1 Data definition list. Data explanation. Global real variables V11, V16. X direction touch sensing position X, Y, Z, R, P, I. Global real variables V21, V26. Y direction touch sensing position X, Y, Z, R, P, Y. Robot language file explanation. Step 1-6 operates X direction search. Step 3 SF1 stops letting the wire touch the workpiece. In Step 4, the current robot TCP position and posture X, Y, Z, R, P, I will be stored in the real variables V11, V16. Step 7-12 operates Y direction search, same as X direction search. In Step 10, the robot TCP position and posture X, Y, Z, R, P, I at the touch sensing point by the Y direction search will be stored in the real variables V21, V26. Step 2 and Step 5, Step 3, Step 7, Y, X, Z, Step 6, Step 8 and Step 11, Step 9. Step 1 Step 12 2.2 linear operation through 4 points specified with coordinate values, 2 to 2. 2.2 linear operation through 4 points specified with coordinate values. This section describes the example of the linear interpolation operation through 4 points numerically specified with coordinate values. In normal teaching, the robot needs to be moved to the teaching point by manual operation. In this example, 4 teaching points are specified with the Cartesian coordinates values in the user coordinate x, y, z, r, p, I, using function command let pose variable letcoord fn 630, fig. 2.2.1 linear operation through 4 points specified with coordinate values, y, x, z, world, x, y, z, user, y, x, p1 200, 600, 150, user, p1, p2, p3, p4, p3 300, 800, 150, P4 200, 800, 150, P2 300, 600, 150. Table 2.2.1 Data Definition List. Data Explanation. Pose variable P1. Linear operation. The first position equals starting position. Pose variable P2. 2 pose variable P3. 3 pose variable P4. 4. Robot language file explanation. Step 2468 Specify pose constants with user coordinate values. Using the function command letcoord. They specify the robot TCP position and posture with the coordinate values in the user coordinate 1x, y, z, r, p, I, and store them in the pose constants P1, P4. Step 3 5 7 9 10 Move it to the position specified with the pose constants. They perform linear operations setting each pose constant to a target point. Though step 3 4 7 9 10 look like a normal move command in the program monitor, they are the function commands fn 645 movex actually. fn 645 movex operates to the TCP position and posture recorded in the specified pose constants. 2.3 Circular operation with specified center point, 2 to 3. 2.3 Circular operation with specified center point 90-degree division. This section describes the example of the task program which operates along the arc of radius, r with the current position as the center, since the arc radius is specified with the real variables. Arc operations of different diameter can be described with one task program. When this task program is used for the operation, such as welding or cutting where the arc operation is done several times changing the center position, the task program will be easy to maintain. P10, V11, V12, V13, P11 and P15 V11, plus L1, V12, V13, P13, P12 V11, V12, L1, V13, P14, L1, Y, X, L1, Fig. 2.3.1 Arc operation of radius L1, mm with specified center point. Table 2.3.1 Data definition list. Data explanation. Pose variable P10. Pipe center position equals starting position. Pose variable P11. Circular operation 0 deg position. Pose variable P12. Circular operation 90 deg position. Pose variable P13. Circular operation 180 deg position. Pose variable P14. Circular operation 270 deg position pose variable P15. Circular operation 360 deg position global real variables V11, V16. Pipe center position X, Y, Z, R, P, I. Local real variable L1. Arc radius mm 2.3 Circular operation with specified center point, 2 to 4. Robot language file explanation. Step 1 initializes each variable. Substitutes the arc radius for the real variable L1. When L1 is changed, pose constants which will follow the arc track of radius L1, mm can be calculated. Step 2 14 Set the each pose constant. First, substitute the current position equals arc center position for the pose constant P10. Step 3 4, for the real variable V11, V16. The current robot TCP position and posture are substituted. Next, calculate P11 to P15. Initialize the each pose constant with P10 equals arc center position. Calculate the pose constants to be the teaching points for the circular arc using L1 equals radius mm. Calculates P11 according to Fig. 2.3.1. P11 is at the position where it moved for L1. mm from P10 equals arc center position to this plus direction. The positions x, y, of P10 and P11 expressed with real variables are shown below. P10 V11, V12, V13, P11 V11, plus L1, V12, V13. Step 6 shows the one written in the robot language. Let P11, M1, x plus equals L1, robot. Step 15:20 perform arc operation. Perform arc operation with each pose constant as the target point. Though step 15-20 look like a normal move command in the program monitor, they are the function commands FN645 MoveX actually. FN645 MoveX operates to the position and posture recorded in the specified pose constants. 2.4 Detection of pipe center position. 2 to 5. 2.4 Detection of pipe center position. This section shows how to detect the pipe center position using touch sensor FDWD. First, it moves to the ideal pipe center position. From the ideal pipe center position, search operation is done twice in the x direction and y direction. The average value of x coordinate value of the touch sensing point in the x direction is set as the x coordinate value of actual pipe center position. Also, the average value of y coordinate value of the touching point in the y direction is set as the y coordinate value of actual pipe center position. 2.4.10 Fig. 2.4.1 Detecting the center position of a pipe. L15, X, Y, P5, P21, P22, P23, P24, P25, P5, P4, P3, P21. Table 2.4.1 Data definition list. Data explanation. Pose variable P2 starting position. Pose variable P4 pipe center position. Reference position only the height direction has been corrected. Pose variable P5 pipe center position after detection. Pose variable P21 search start point comment is plus, minus, I plus, I minus. Pose variable P22 teaching target point for plus direction search. Pose variable P23 teaching target point for minus direction search. Pose variable P24 teaching target point for I plus direction search. Pose variable P25 teaching target point for I minus direction search. Global real variable V1. Pipe inside diameter mm. Global real variable V3. Pipe height from reference plane mm. Global real variable V21. Wire extension length. Global real variable V22. Z direction retracting distance mm. Global real variables V30, V35. Pipe center position after detection x, y, z, r, p, I. Global real variables V50, V55. Starting position x, y, z, r, p, I. Global real variables V130, V135. Plus direction touch sensing position x, y, z, r, p, I. Global real variables V140, V145. Minus direction touch sensing position x, y, z, r, p, I. Global real variables V150, V155. I plus direction touch sensing position x, y, z, r, p, I. Global real variables V160, V165. I minus direction touch sensing position x, y, z, r, p, I. Local real variable L11. Pipe inside diameter mm divided by 2 local real variable L12. Wire extension length mm divided by 2 local real variable L13. Z direction retracting distance mm equals V22. Local real variable L15. Searching operation Z coordinate value equals pipe height from reference. Plane wire extension length /2 2.4 Detection of pipe center position 2 to 6. Robot language file explanation. Precondition Condition 1 When this task program starts, TCP must have moved to above the ideal pipe center. Condition 2 The height of the pipe top face must have been detected. This is for touch sensing of the pipe inside. If the height is not detected, correct touch sensing cannot be achieved. Example, searching failure. Nozzle interference to pipe. Step 1:8 initializes each variable. Step 9:17 sets the each pose constant. First, substitutes P4 for P2125 and initializes it. Step 18:40 stores the searching operation and the touch sensing point in the real variables. Performs touch sensing in the 4 directions of plus direction, minus direction, I plus direction, and y direction. In the searching operation in the each direction, it stores the position and posture of the touch detection point in the real variables as follows. Plus direction V130, V135, minus direction V140, V145, I plus direction V150, V155, I minus direction V160, V165. Step 41:54 calculates the pipe center position from the touch detection point. calculates the actual pipe center position from the touch sensing points of the four directions of S plus direction, S minus direction, I plus direction, and Y direction. X coordinate value of pipe center position V130 plus V140 divided by 2 Y coordinate value of pipe center position V151 plus V151 divided by 2. Next, it stores the actual pipe center position in the pose constant P5. 2.5 circular operation with specified center point, 2 to 7. 2.5 circular operation with specified center point 45 degree division. This section describes the program example where the teaching points for the circular arc are divided into 45 degrees on the basis of the task program of 2.3 circular operation with specified center point 90 degree division. Fig. 2.5.1 arc operation of radius L1, mm with specified center point, y, P10, V11, V12, V13, P11 V11, plus L1, V12, V13, P15, P13 V11, V12, L1, V, P18, 13, P12 V11, plus L3, V12, L3, P14, V13, P16, P17, L1, X, L3, L3, Table 2.5.1 Data Definition List, Data Explanation, Pose Variable P10, Pipe Center Position equals Starting Position, Pose Variable P11, Circular Operation 0 Deg Position Pose Variable P12, Circular Operation 45 Deg Position Pose Variable P13, Circular Operation 90 Deg Position Pose Variable P14, Circular Operation 135 Deg Position Pose Variable P15, Circular Operation 180 Deg Position Pose Variable P16, Circular Operation 225 Deg Position Pose Variable P17, Circular Operation 270 Deg Position Pose Variable P18, Circular Operation 315 Deg Position Pose Variable P19, Circular Operation 360 Deg Position Global Real Variable V11, V16, Pipe Center Position X, Y, Z, R, P, I, Local Real Variable L1, Arc Radius mm Local Real Variable L2, 21.4142, Local Real Variable L3, Arc Radius /2 Circular Operation with Specified Center Point, 2 to 8, Robot Language File Explanation, Step 1.5 initializes each variable, substitutes the arc radius for the real variable L1, when L1 is changed, calculates the pose constant which will follow the arc track of radius L1, mm. Also, to calculate the arc teaching point every 45 degrees, it substitutes the value calculated by dividing the arc radius by 1.4142 for real variable L3. Step 6.29 set the each pose constant. First, substitute the current position equals arc center position for the pose constant P10. Step 6, for the real variable V11, V16, the current robot TCP position and posture are substituted. Next, calculate P11 to P15, initializes the each pose constant with P10 equals arc center position, calculates the pose constants to be the teaching points for the circular arc using L1 equals radius mm and L3 equals radius divided by 2, calculates P12, according to Fig. 2.5.1. P12 is at the position where it moved for L3, mm from P10 equals arc center position to this plus direction, and for L3, mm to the I minus direction, the positions x, y, of P10 and P12 expressed with real variables are shown below. P10 V11, V12, V13, P12 V11, plus L3, V12, L3, V13. Step 11-12 show the one written in the robot language. Let P12, M1, x plus equals L3, robot let P12, M1, y minus equals L3, robot. Step 30-39 perform circular operation. Perform arc operation with each pose constant as the target point. Though step 30-39 look like a normal move command in the program monitor, they are the function commands FN645 MoveX actually. FN645 MoveX operates to the position and posture recorded in the specified pose constants.